So I'm going to be talking about our work, which is called Transaction Fee Market Design for Parallel Execution. And I'm Lioba, and this is joint work with Bahar Acılan, Andrei Constantinescu, and Roger Wattenhofer. And we're from ETH Zurich, Definity, and Category Labs. So let us start with some context here. So consider we have the block here that has 4 transactions in it. Now, historically, in all blockchains, what we would have done if we were to execute these 4 transactions, we would have executed them one after the other sequentially in the order that they were executed in. However, parallel execution is much more common in blockchains today. And the motivation for that is clear, because we can scale throughput without really increasing hardware requirements, because all customer hardware these days comes with at least a couple cores. But also at the same time, we shouldn't be getting ahead of ourselves. This all maybe sounds a bit too perfect. Well, can we just parallelize and then we can increase throughput? But what is the throughput that we can actually hope for? Because if 2 transactions, if they write to the same state, for instance, they both want to trade in the same liquidity pool, it is at least not very straightforward to execute them in parallel. And in Ethereum, as you can see in the depiction here, many transactions actually do interact with the same state in the block. So on the slide, what I'm showing is an address-based graph representation of a sampled set of Ethereum transactions. And each vertex here is essentially an address, so a contract or a wallet, and the edges are transaction calls. Now, any transactions here that are sort of in a connected component, they're at least difficult to parallelize. And you can see that in these connected components, sort of the highlighted addresses, it's many of the biggest DeFi applications. But still, despite this big interconnectedness, at least a 4-fold speedup should be realistic, maybe even more if we do something a bit more complex. Okay, so then the question that we really wanted to ask in this work is, okay, we can parallelize, but is there anything else that we need to consider when moving to parallel execution to gain this increased throughput? And in a sense, the question that we're asking is it enough to parallelize the execution layer? And our answer to this is that it's really not enough on its own. What we also need is a fee market that is designed with parallel execution in mind. So this is important such that transactions that hinder parallelization are charged more than those that facilitate it. Or to put it differently, we want a fee market that should incentivize parallelizable transactions. And in this work, that's the design space that we explore. Now, before I get to the core of our work, I want to take a quick step back, though, and explain what I'm talking about when I refer to a fee market. So a fee market establishes a fee that a transaction will pay for inclusion. And it's a key component of every blockchain protocol. Now, there's some desirable properties that a fee market should have. The fee should be higher for more complex transactions, and it should be higher during periods of high demand. Now, these 2 requirements, they're typically decoupled. And in response to that, what we did is we introduced the following framework to talk about fee markets in this work. So consider that we have a transaction here. And now this transaction first enters what we call a gas computation mechanism, or GCM for short. And this measures the load that this transaction imposes on the networks in terms of parallel execution. And the outcome is then expressed in units of gas. Essentially, what this GCM will ensure is that the more complex transactions, that they pay higher fees. Then the transactions enters what we call a transaction fee mechanism, which then, among other things, associates a cost with each unit of gas. So ensuring that fees are higher when demand is high, when the demand is high. So the second property. Now, for an example fee market, let us look at the current fee market that is utilized by Ethereum and to see how this fits in the framework. So in Ethereum, a transaction fee is comprised of units of gas that the transaction consumes. So this would be established by the GCM multiplied by the price of each gas unit. This is then established by the TFM. And now in this work, we will focus on the gas computation mechanism, so to assign complexity to a transaction. In the current fee market utilized by Ethereum, this execution component of gas can be seen as a proxy for time. And this execution component of gas in particular is what I'm focusing on throughout this talk. So from now on, when I'm talking about gas units, I am referring to this execution component. Okay, so the next thing is that, well, what I led this talk with is that the current fee market maybe is not the best, where we have the proxy for time in the gas units. in light of parallel execution. So let's see why this is the case. So we have a transaction tx1 here, and tx1, it takes 6 units of time to execute, and it interacts with 6 storage keys. So this is, for example, reserves in a liquidity pool. And throughout this presentation, we will assume that these storage key accesses, they're known in advance. And for us, this will be everything that we need to know about these transactions. Now, in this model, we're making some simplifying assumptions. For example, we do not differentiate reads and writes, but it still provides a good first approximation of the real world. And then what we can do is we can draw each transaction as a rectangle. So here on the y-axis, we now have the execution time of the transaction. And on the x-axis, we have the storage keys that the transaction accesses. And when we then look at how many units of gas this transaction would cost, this would take 6 units of time to execute, and therefore it will cost 6 units of gas. Remember here that we're considering really just the execution component of gas. And now we have a different transaction. We also have tx2 here. And tx2 takes exactly the same amount of time to execute, but tx2 really just accesses 2 storage keys. And then, however, with the current GCM that is being used, tx2 also would cost 6 units of time, as it takes 6 units of time to execute, and the current mechanism doesn't look at how many of these storage keys it is accessing. And this is perfectly fine as well when we're executing transactions sequentially, because if we're executing in a single thread, it really doesn't matter how many storage keys are being accessed. But now when we move to parallel execution, it is clear that the transaction on the left is harder to parallelize than the one on the right, as it's locking more keys. So now with this in mind, what we looked at is what properties would we even want from a gas component in a fee market in order to be able to support parallel execution. So in a sense, to make transactions that are easily parallelizable, incentivized. Or to ask this question differently is what kind of transactions should be consuming more gas than other transactions? Now, I'm going to start with some very natural monotonicity properties, and let's start with one based on the example that we already seen. This is what we call storage key monotonicity, and essentially what it demands is that if we have 2 transactions that take the same amount of time to execute, and if one of them uses only a subset of storage keys of the others, it should consume less units of gas. So now example here, tx2 should consume less units of gas than tx1. And this is quite intuitive why we would want this property to hold, because if we weren't charging tx1 more, people would might just add or consume more storage keys in their transactions and hurting the network by that without paying more. Now then we have another natural monotonicity property that we want to hold as well, which is time monotonicity. So again, we have 2 transactions here. Now they consume exactly the same set of storage keys, but they take different times to execute. So tx1 takes 6 units of time and tx2 only 2 units of time. Now in this case, we would want that tx2 consumes less gas than tx1. And again, it's quite intuitive to see why this property is desirable, because we would want that a transaction that takes more time to execute also consumes more gas. Otherwise, you could just make your transaction longer, execute for longer, and you wouldn't be paying for this extra effort. Now, the final property that I'm going to be outlining in detail here is what we call transaction bundling. It's a bit more complex than the previous 2, but we now have 2 transactions, tx1 and tx2. They're both shown on the right here. And the highlighted parts in the transaction essentially shows at what points in time they're doing execution on which storage key. And on the left, we're now seeing the sequential composition of these 2 transactions. So how a transaction would look if we were just executing first tx1, then tx2, and putting it into one transaction. And now in this example, what we would want to be the case is that the sum of the 2 individual transactions of gas they consume, that should be less than that of the sequential composition. The reason why we want this to hold is that the bigger one should be harder to schedule than the individual ones, so harder to parallelize. Now, we also have some additional properties. I'm not going to go through all of them, but go quickly through some additional key properties so that you get an intuition. So one of the remaining ones is schedule monotonicity, which demands that transactions with higher marginal contributions to the execution time should consume more gas. We also have efficiency that ensures that gas consumptions of transactions in a block should collectively account for the total time needed to execute the block. And we have easy gas estimation, which ensures that the transaction submitter should be able to estimate a transaction's gas consumption in advance. Now, the next natural question that you might ask, given that we have this wish list of properties we would want for a GCM, is it even possible for a mechanism to achieve them all? And unfortunately, it is not the case. In particular, what we show in our work is that there's no mechanism that can have both easy gas estimation and schedule monotonicity, unless it's the constant mechanism. And also, it's impossible to have both easy gas estimation and efficiency. I'm not going to go through the details here, but sort of the high-level intuition is very easy to follow. So essentially, what easy gas estimation requires is that the gas consumed by a transaction does not depend on the other transactions in a block, because then it's no longer easy to estimate the gas that it's consuming. While in order to achieve the other two properties, we must actually be looking at the other transactions in the same block when assigning gas to a transaction. So based on these impossibility results, it appears a bit as if this easy gas estimation might actually be the problem. So I want to spend a bit of time to say why we would maybe want this property in the first place. If you recall, easy gas estimation ensures that a transaction submitter should be able to estimate a transaction's gas consumption in advance. Now, this is important in and of itself. It makes it easier for users to estimate the fee of their transaction, but there's more to it. As shown on the slide now, again, the GCM is not the entire fee market. We also have the TFM that assigns the price per unit of gas. And the TFMs, they've been extensively studied in prior work. And easy gas estimation is essential for a seamless composition with existing TFMs. So what I mean by this is that easy gas estimation is needed in a GCM in order for us to be able to retain the properties of existing TFMs when it's now composed with a GCM. So easy gas estimation is essential to retain these properties of existing TFMs. What are these properties? For example, one is that we want them generally to be incentive compatible for users as well as for block producers, which just means that no party should be able to increase their result by deviating from the intended protocol. Then we also want them to have good welfare guarantees and to be resistant to off-chain agreements between users and block producers. So this means that we don't want to make it possible for users and block producers to collude and thereby increase their expected outcomes. So these are all standard TFM properties, which we actually know that they cannot hold at the same time. But still, we have TFMs that exist in reality, which give us a good sort of subset of these properties. And easy gas estimation is key for us to retain that. But at the same time, as we saw, it blocks us from achieving those properties that most directly ensure that transactions are charged according to how parallelizable they are. So now what we did when exploring GCMs is we then, given sort of this reality, we wanted to consider mechanisms in both worlds. So those with easy gas estimation and those without. And then for each mechanism, what we did is we assessed how they fare in all our properties that we want to hold. So on the left, you can see those with easy gas estimation highlighted in yellow, and on the right are those without easy gas estimation. Now, this is a big table where green essentially shows when a property holds and red shows when it doesn't. I'm not going to go into the details of the various mechanisms we explore in the interest of time. What I'm going to do instead is focus in on some promising GCM candidates, and then present a suitable fee market that integrates this candidate, starting with one that actually has easy gas estimation. So how would this candidate fee market look? Well, for the GCM, we can plug in what we refer to as the weighted area mechanism. So the gas a transaction consumes is the time it takes to execute multiplied by the weights of the storage keys that the transaction consumes, so the sum of them. And here, weight per storage key the weight that we assign to a storage key is essentially supposed to approximate the demand on the key. And it could do that based on historic demand. Why do we believe this could be a promising candidate? Well, if we go back to this table, what you can see if we now look at the weighted area GCM is that it actually achieves all of the properties it can, given that it has easy gas estimation. And now coming back to our candidate fee market, for the TFM part, given that we have easy gas estimation here, we can use whatever TFM we want. For instance, the EIP 15591, which is the current one deployed in Ethereum. So this would be one complete picture of a candidate fee market for parallel execution. Then we can also look at the other side, so at those mechanisms without easy gas estimation. There, the one that I'm going to be focused on is what we call the time proportional make span GCM as a concrete candidate. So the TPM, what it does is that it allocates gas to a transaction in proportion to the transaction's execution time relative to the total block's execution time under a specified scheduler. So what it does essentially, it provides a simple way to align the gas consumption with how transactions constrain parallel execution in a block. Again, why is this a potential promising candidate? Well, if we go back here to our table and we look how the TPM fares, which is now highlighted here, you can see that it actually achieves all properties it can, given that it doesn't have easy gas, given that it has efficiency, but schedule monotonicity. So now coming back to our candidate fee market, it gets a bit more complex because for the TFM part, we can no longer just use our favorite mechanism as a black box without easy gas estimation, as well, these properties that we have there are no longer guaranteed to hold. And first, this is an area that might be interesting to explore in future work for what we could do on this side. Now, the question is probably which way should protocols go? So should they go the route with, or should they go the route without easy gas estimation? And this essentially, ultimately, it depends on protocol level priorities. So what you get with easy gas estimation is you maintain the user side simplicity and compatibility with existing TFMs through easy gas estimation. And it also makes the implementation a lot easier. On the other hand, if you're pursuing this block level efficiency and a more accurate resource pricing, at least for the storage keys, the cost of this would be at the cost of giving up the previous benefits. So it would involve more work, development to be done, but it would also ensure more accurate pricing. And ultimately, this will depend on sort of the protocol priorities. Now that brings me to the conclusion. So what we did in this work is we distilled a list of properties that we want to hold for GCM in light of parallel execution. Then we explored the design space of GCMs and identified promising candidates. And finally, our work is of theoretical nature here, but we hope that it could pave the way to practical implementations of GCMs for parallel execution that are needed to unlock the full execution layer potential. So these are my contact details and also a link, a QR code to the paper, and I'm happy to answer any questions.
Okay, we do have time for questions. Okay, yes.
Hi, thanks for the talk. In the weighted mechanism, if those weights are computed from historical transaction data, can we really say it's an easy, I forget what the terminology was, but
easy gas estimation?
Easy gas estimation.
Yeah, I guess you would assume that there's like an easy like RPC call you could do for the node that like exactly gives you this. If at least like with a 12-second block time, that should be sufficient, for example. Now, if we're moving to like high throughput chains where we have very short block times, I do agree that it might be a bit more difficult. I guess you could delay the update to allow for that, for example.
Thank you.
Thanks.
Okay. Thank you. Awesome talk. Quick question for you. One of the things that's interesting in parallel execution is you can actually reorganize the execution trace, and that can sometimes get you some results. For example, you might be able to pipeline some stuff. Did you consider that in this general mechanism? Like, is this one of the things that you considered when you were saying like this is what do you call it, incentive compatible, for example, for the miners?
So just for me to reword your question, is that but to make sure I understood it correctly, is that, well, if you start parallelizing and you change the execution order, then outcomes will be different.
Right.
Yes, so to some extent, we do not consider this explicitly, but sort of the scheduler is, well, you can define properties it should have. And one property you could define is that the miner gives this order and the scheduler has to abide by it.
Got it.
This would, of course, constrain how much you can parallelize, but it would be maybe like a mix of both worlds. You could, okay, the miner still has sort of the max profit from the block it created, or like the validator, the block producer, but at the same time, you can get some parallelization benefits.
Awesome, thank you.